Yeah, I think recording has started. So, welcome everyone. Today, in our group meeting, Souradeep Sasmal will present. And Souradeep did his PhD from Bose Institute. And after that, he did his postdoc in IIT Hyderabad. Now he is in China, in the Institute of IFFC USTC, Chengdu, Republic of China. Today, we will talk about shared randomness, how to certify it. So, now I think you can.
Okay.
You can start. Yeah.
Okay. So, good day, everybody. Today, I'll be talking about randomness, not shared randomness, but we told. So, what is randomness and how we can certify it and quantify it. So, I will start with the very basics of the concept, and let's see today how far we can go. Otherwise, I will continue. I can also continue in the next week. So see, randomness is everywhere. Randomness is very fundamental to many many applications, like in information processing, like key distribution, secure communication. There you need a secure and private and proper random number to do all those processes. And apart from the information processing task, randomness is also important in some scientific experiments like loophole free bell test that people know, because if the the input random number is not random, then it can be shown that any any bell violating statistics can have a local ontic model. And also it is very important in the medicinal study where the random sampling is very important for drug testing and all those things, or weather prediction, different kind of different area randomness found many applications. Mostly important in the policy making or the distributions of wealth also, proper random input is important. Otherwise, the policy or those distribution of wealth process can be little bit skewed to some group, the which is usually the reality anyway, because we don't have a good random number or good intention. And just to give you the importance, the Aadhaar Act says that the number should be a random, but they don't define how to get a random number. So we don't know. So until unless we understand what is random number, then there is always a security vulnerability in these things. So you see the problem. So basically, what is randomness is we understand that lack of pattern or predictability of some events. We can say that okay, this is at random. But the real problem is how to be sure that one sequence of number is random or not. For example, if you see this famous cartoon that this animal is a random number generator, he is always giving the output 999999, but we don't know whether there will be any number or not other than 9, so that the whole sequence become random. So we first have to solve that how we can certify randomness, and then how we can quantify it. I can give you more examples. For example, if you see these three sequence S1, S2, and S3, you can see that S1 sequence, one can easily understand that. Yes.
Souradeep,
Yes.
Can you make this full screen? This is not full screen yet. Your screen.
Yeah, I know it is not
make
full
the
screen.
PDF.
Yeah. Is it?
So it is a little smaller. So okay, no problem.
No, still not. Okay. Wait. Where all the logos? Okay, let me open this presentation one more time.
Yeah, it's fine. It's fine. It's fine. Please continue. It's fine. I guess only me. I'm watching it on mobile phone, so that is why the problem is only for me, I guess. So Not a problem. Please continue.
Yeah. Now you can see the full screen.
Now it's perfect. Now it's perfect.
Yes. Perfect. Please.
Now it's perfect. Yeah.
Okay. So yeah, so if you look into these three sequence like S1, S2, and S3, by looking into S1, one can easily say that okay, S1 is basically the repetitive pattern of 0, 1, 0, 1, 0. So S1 sequence is not random. There is a pattern in there. But what about S2? That I don't know. And for about S3, it is little bit hard to say that whether the pattern in S3 is random or not, because it's a little bit complex than the sequence S1. But if eventually one can search it in computer, they will find that basically S3 is composed of this. There is a pattern in S3 which is a repetition of some blocks. So and about S2, there is no such pattern. We don't find any pattern in S2. So, and one can think that S2 is generated by flipping a coin 20 times, or maybe we project the electron in a standard lab setup, and when it goes up, we put it 0, and when it goes down, we put it 1. In that way, we can generate this sequence S2. Huh?
Hello, Souradeep. So, can I think this way that for this S3, I don't know about these things much, but in the S3, you see there is a lots of 1 and very few are 0. Okay.
Okay.
So, in that case, can I from this existing pattern, can I guess like that? Okay, since 1 is higher frequency, so the next one could be 1 with higher probability, and 0 could be lower probability. And since the probability is not half-half, so that's why it is not a random. In that way, can I say?
Maybe if you know the pattern, you know everything. So you know that you can definitely know what is the result you will be getting if you can design, if you know the pattern. So it is nothing to do with the 0, 1 or random or not, but you know the pattern already, right? So then when you know that what the pattern, it will follow as a pattern. So there is no randomness left.
So yeah, to answer the mid question that you are trying to say how to check a sequence is random or not, that is maybe one way to check it, right? That you count the 0 and 1 and you find the probability is what, and then you can try to predict which will be the next element. But this is some method, some hit and trial method, and the basic thing is there is no pattern in S3. I mean, there exists a pattern in S3 that basically the smallest block in S3 is the blue color block. What I wrote in down that now one can ask that 0, 1, 1, this blue color block is a random sequence. Yeah, it may be the blue color block, maybe a random sequence, and then it may generate from the style as S2. But still, if I have a long sequence, then it is very hard to tell whether the sequence is random or not, because it depends, ultimately it depends on the minimal block decomposition, this kind of thing. It will depend on that, whether we can break it in a minimal block or not. And if we can't, then we can't say. There are some so and also another important thing about is the origin where the sequence is producing. For example, that I said that S2, the sequence of S2 is originated from some underlying physical process, and another thing about randomness is it should be patternless, what I already talked about. Now let's talk about a little bit about the origin, because let's say this underlying process, if that process is deterministic, then whatever we see, this is not a true randomness. For example, this flipping a coin, is it really a random process? It is not, because if I know the amount of force I am giving into the coin, and if I know the air resistance and all that, then I can actually count the number of flipping by calculating the maximum height from the Newton's laws of motion. And then with deterministically, I can say what should be the outcome of the coin. And in that way, you see, even if there doesn't exist any pattern for S2, still the sequence is deterministic. I mean, before you start your coin tossing experiment, I can write the sequence S2. So in that way, S2 is not random. So we have to figure out a process where we can trust the origin also, and also we can make sure that the sequence is inherently random, even without checking the sequence in a computer. So it should not depend on the complexity of the problem. Yeah.
Can we think of it is that in this way, suppose you have a sequence, a finite sequence, and we know that whether like some kind of pattern exists or not, in the beginning we don't know. But as like, but we can test like which which pattern would be more likely to emerge if we expand on X1, if you consider the sequence, right? We can calculate that, right?
Yes, you can try to find a likelihood pattern and try to compare with that. This is all things are the method to test whether there exists a pattern or not in a long running sequence. And we don't have to think about method 1, method 2, method 3. Actually, there are a lot of work people have already done, and it is under the setup called NIST. They actually test whether a sequence has randomness or not, but still, a computer can only search over a finite number of patterns, right? And from mathematics also, you can have a generation of randomness. One may argue that, let's say, the digit of the pi is completely random. But the thing is, okay, that I know digit of the pi is random. But if I use that random number in a security, all the adversary will know what are the numbers, right? Because all the adversary can access the function pi, and then they can just reproduce those numbers. So even if there is no pattern, the source is not reliable there. So any random number which is originating from a mathematical function, it cannot be certified, because if adversary knows the function, then they know the random sequence.
Yeah, this is a good point, Sasmal. That's a very good point. And yeah, if you can, you know the mathematical function, you can always simulate the randomness. So that's not a problem. But it looks random, but still it is simulably random.
Right.
Yeah.
And also we never know if there is a pattern or not in the pi. But one may say that, okay, right now our understanding is pi doesn't have pattern, so let's take it as a random number. But the origin is very problematic. If I know the origin, I know everything. Now, some people can come up with an example that what about radioactive decay? We understand that, okay, pi may not work, coin toss may not work. What about radioactive decay? And also the radioactive decay sequence can pass this NIST test. So that means that sequence is patternless and random. But the problem with radioactive decay is different, little bit different. That is the problem with the radioactive decay is, let's say I am an experimentalist, and with the radioactive decay experiment, I found one random. Hello? Yes. Yes. Hello?
I think he's not saying something. Suddenly mic was someone on.
Okay, so if okay, I'll just continue. If you can ask the question, just stop me. So let's say I'm an experimentalist and I produce a. What is happening? Let's say I'm an experimentalist and I produce. Wait, there's something is wrong. Yeah. No. I can. Okay, let's say I produce a sequence of number using the radioactive decay, and that number is a random. But the problem will be
Hello,
that,
Souradeep.
hello, yeah,
Hello,
hello, yeah,
can you hear me?
yeah.
Yeah, yeah. So, what is this NIST test, Souradeep?
What the actual test is, I don't know, but what they do, that is, if you have a sequence of number, you can give them, they can check whether that sequence has a pattern or not. And they do with some different complicated mathematical functions
Okay,
and
okay.
searching over different methods, some kind of a internationally accepted test that if someone use a
Yes.
random sequence in a cryptographic test, it has to be NIST pass. And there are
Okay, okay, okay.
some parameters also.
Okay, okay, okay. Fine, fine.
Yeah, so let's say a sequence is produced with a radioactive decay, but the problem is one can store that sequence in a memory, and if they sell that sequence to a user will go to the NIST and will ask them if the sequence is random or not, and the sequence will pass the NIST test. But the problem is whenever user will try to use that sequence, the producer will know what the sequence is because it is already stored in a memory. So even if radioactive decay is a random process and we can use that to produce a random number, but the problem here is the privacy or the secrecy. So basically, the existing random number generator can be categorized as in this manner, that mathematics-based and physics-based. Mathematics-based random number is called PRNG, that is pseudo RNG, and you know why it is pseudo, because the origin is not trusted, and their secrecy actually depend on the computational power of the adversary, and also adversary is unaware of the underlying arithmetic operations or algorithm. And if there is any underlying pattern that we don't know, or even NIST don't find out, but still it will create many problems in those applications if we use this sequence. And then the next category is the physics-based random number, which is divided into two parts, device-dependent and independent. And for device-dependent, one is the classical mechanics-based random number generator. People used to tell it as true RNG. Why this is true RNG, I don't know, because maybe it is introduced after the pseudo RNG, so that's why people name it like true RNG. And they rely on some physical processes, like I just told, the tossing a coin and something like that, or maybe one can use some more complex process which are hard to calculate. But really, these processes are not random, because classical mechanics allows you to calculate all the outcomes in a deterministic way. Maybe the calculation will be hard, but in principle one can calculate. So this type of randomness is called apparent randomness, where actually the randomness I see by coin toss or something like that, that is because of our ignorant. It is not the inherent randomness present in the process. And the next one is again the device-dependent random number generator, which is called QRNG, quantum random number generator. It's a very, very simple process. You have a electron. If it passes through a standard lock, it will go up and down. Here I'll given an example with, this is some, let's say, some photon and beam splitter with transmission and reflection coefficient half. Then it will be either detected in the up detector or in the down detector. Yes.
So you tell now that in the case of radioactive decay, one can write down that numbers, and if someone try to use that random number, then actually who wrote it down can have access of these random numbers, right?
Right.
So if one use that radioactive material directly to generate random number, then what prohibits him or her?
Then it's okay. But I doubt that whoever the persons who are writing the Aadhaar Act in the parliament, they don't use the radioactive decay experiment.
No. In case.
So your random number, yeah. So your device should be something like that. I don't have to trust my device. I will press the button and it will give me my desired result, just like a calculator. right? So yeah, so obviously, if one can use the radioactive experiment in their lab and then produce that to use for his bank password, then it's completely fine.
Okay.
We don't have any problem.
In that case, we can categorize it as a QM based, right?
Yes, basically it falls under the QRNG and device dependent
Yes.
QRNG. Here also the same criticism is there, and just for completeness and just telling you that why this process is random, because if we accept the standard interpretation of quantum theory, then according to the second postulate, that since the value doesn't exist before the measurement, so actually we can't predict the outcome with certainty. So in a way, Bond rule certifies the inherent randomness. Or some time ago, Mead pointed me out that it will be more convenient to say the existence of the lower bound of uncertainty principle is actually gives you the proper randomness, and it is more trustworthy than the classical mechanics based random number generator, because here you actually cannot predict the outcome. But the same criticism is still there. If one write down all the sequence and then try to use it, then it can be matched. So other than that, also there are some other criticism. That the first criticism is how to guarantee the privacy, and another criticism is, let's say I know the supplier, I trust them, there is no adversary, it's a real world, ideal world scenario. But still, if my QRNG deviates from the intended design, then how can I be sure that my QRNG is working properly or not? Because that can happen for many reasons. There may be some noise, unavoidable biases, anything can be happening. And the last one is the foundational guy always asks that whether there is an ontic model or not. For example, for qubit statistics, John Bell constructed an ontic model. So basically, we can predict all the statistics from qubit. But for higher dimensional system, one can have a statistics which cannot be predicted. Still, these first two criticism will be still there. So to have a foolproof random number generator, we need some characteristics on there, that I don't have to trust the inner working of the device, and I don't have to trust the supplier, and also the numbers generating from that device must be private. That means it cannot come from a previously stored strategy. Okay, so there comes the device independent random number generator, what I call GRNG, genuine random number generator. So because this is the most reliable one. So how we can certify randomness? That for that reason we have to consider the Bell scenario, and Bell scenario gives many foundational perspective. But here I can use the Bell scenario in a little bit different way. Let's say we have we have two parties, Alice and Bob. Alice and Bob, and their labs are into different light cones, so they can't communicate with each other. And let's say Alice has some input X and output A. Okay, and what they do, they just press some button and get some output, and they can characterize this probability distribution A, B, X, Y. And let's say there is some preparation procedure which prepares the state for Alice and Bob. So they can actually characterize this joint probability distribution, which we'll call it as behavior. Behavior is a vector in a real number space, and it belongs to basically in a real number. Let's say Alice has n number of measurement settings, Bob has nb number of measurement settings, and let's say Alice has outcome B and Bob has outcome T. So usually this behavior, and this is a convex set also. The set of joint probability distribution is a convex set, and if there is finite number of external distribution, then this will form a polytope. I will talk about it later. So now in this operational paradigm, I mean in this experimental scenario paradigm, we can define two assumptions. Like one is predictability, because we want our statistics to be random. So that's why I start with the assumption predictability, when the statistics will be predictable. If each outcome probability or belongs to either 0 or 1. So that means at each run of the experiment, I can predict the outcome of those measurements, X and Y. And number 2 is no signaling. No signaling states that the statistics of Bob should not be affected by Alice's choice of settings and vice versa. Alice's measurement statistics should not be affected by Bob's choice of measurement settings. So we can write it like that. P of AX should be equal to P of AXY for all AX. And similarly for Bob, we can write the same equation that it should satisfy this. Now it's a simple algebra and use of Bayes theorem that if we apply this to assumption, we can factorize the joint probability. We can factorize the joint probability, and if we calculate a functional, which usually we call it as a Bell functional. If we calculate, for example, let's say if we consider a CSSH functional. Why I am considering CSSH functional? There is a point of interest because this predictable no signaling theory has a finite number of extremal points. So this predictable no signaling theory is basically forms a polytope like this. This belongs to a R8 and it has this predictable no signaling, has total 16 vertices. And just for simplicity, I am drawing in a 2D plane that these 4 corners are the predictable vertices. If we only consider the no signaling set, that whenever the behavior belongs to a no signaling set, it doesn't have to satisfy the predictability condition. If we just only satisfy the no signaling condition, then the polytope look like this, and then it has 24 vertices. 16 vertices are the predictable one, and 8 vertices are the PR box. PR box distribution is here. So if we consider the predictable, this is P plus NS, and this is only NS. And with these vertices looks like this. Since it is predictable, only one entry will be 1, and that one can be anywhere. I'm just writing an example, and other events probability should be 0. And in that way, one can characterize these 16 vertices, and from there one can construct this plane, which hyperplane, which connects these 2 vertices. And it turns out that this plane's equation is basically CHSH is equal to 2. So if I have a statistics whose CHSH value is less than equal to 2, then that statistics must come from here. And if behavior, I mean the set of joint probability distribution comes from inside this box, comes from this box, then these distributions are always predictable. Why? Because let's say maybe this distribution doesn't have this kind of box. Maybe this distribution has something like this kind of box. I'm just writing randomly. So, but this distribution can be reproduced by taking a convex mixture of these and these, one can see, and it can be produced in many different ways. Just an example that it can be produced by this. And since these are predictable distribution, so by knowing the convex mixing parameter, I can actually predict the whole distribution from these 2 vertices. So in that way, whenever a statistics will satisfy CSSH inequality, that statistics is predictable. completely predictable. But when it violates CSSH inequality, that means if the value of CSSH is more than 2, then the distribution must come from somewhere in that region, which is outside the box. And then we can't reproduce that distribution by only taking the convex mixture of the predictable vertices. So that means some amount of unpredictability present in there. Now, how much unpredictability is there? That is a different question. But at least we can say that those distributions are not completely predictable. And since you can see that the okay. Since you can what I wanted to talk about it. Since you can see that this way of looking into the randomness is a completely theory independent, because I just started with the assumption of we have some probability distribution and we have two assumption, predictability and no signaling, and it should, with this condition, the CSSH value should be less than equal to 2. So that means whenever CSSH inequality will violate, then we can say that assumption of predictability is violating, because no signaling cannot violate. So this certification method is completely theory independent, and also that's why we call it as a device independent, because we don't have to know what is inside the box. We will just, if Alice and Bob are the user, they will buy the boxes from a supplier. What they will just do in their home, they will just press some button and get some outcome. So this way of generating a random statistics is more reliable than the QRNG or the other type of random number generator. Yes, one can always say the performing Bell experiment is a little bit difficult, tricky, and that's a different kind of criticism is there. But still, with the growing up technology, maybe someday the Bell inequality experiment will become more straightforward or more popular.
Souradeep, I have a question. So here for the Bell experiment, you need also the input to be random, right?
Yes, I will come into that. That there is a vicious cycle about this, that to produce reliable random statistics, you need input randomness, right? So what we want, or what we have to do, that the requirement of input, what is happening there? So the requirement for input randomness, Ri, should be less than output randomness. Then we can say, okay, Bell experiment gives you a certain way to produce randomness. Now this Ri doesn't need to be reliable. Adversary can know. I mean that our input can come from a radioactive decay, and you can store it in a memory, and then you just use it, right? But it has to be patternless. That's the thing. It doesn't have to be private, right?
So it has to pass the NIST test.
Yes. At least it has to pass the NIST test. Also, NIST test doesn't guarantee that whether a sequence is random or not. I mean, if a sequence fails NIST test, we can say, okay, this has pattern. But if it doesn't, if it doesn't fail, then we should not say anything about it. But people are taking it as a random distribution, something like that. I mean, from free will, you can see that if from my mind, if I choose like randomly, right? Now one can always argue that in this society we don't have free will and all that, but it's still a debatable question. So anyway, so even if we require an input random distribution to perform the Bell experiment and to get a random statistics, our goal is to be like that. Let's say we have total n number of rounds. So in the n number of rounds, we are using this amount of randomness as an input, and let's say we are generating randomness output for some small m number of round, m into RO, and this should be greater than this. Then this is a useful experiment. Otherwise, it is not. So this type of particular thing, when it will be useful or not, or what kind of input randomness we should use and all that, It's related to a topic called randomness expansion.
Okay. Okay.
And
Thank you. Please continue.
yeah. So
Also, Souradeep, yeah.
Yes.
Hello?
Hello, yes.
Yeah, can you go back to the previous slides?
Yes.
Uh, the previous one.
Yes.
Yeah, so here, so this, here the randomness that you are talking about, PAB, ultimately the output randomness that you did, that is
Yes.
the global kind of randomness, right? It's the joint AB, the randomness in AB, that is
Yes.
what you're talking about, right?
Yes, but you can also actually for the cryptographic applications, the local randomness is far more important than the global one, right? For other applications, maybe global one can use, but if the global joint probability distribution violating the predictability condition, then the local probability distribution will also violate the predictability condition. So if there exists a global randomness, the local outputs are also random, or the other way around. If you can ensure the local outputs are random, then your global output will be also random.
Yeah, but no, what I was saying is you said this Ri should be less than Ro, right? But like we can think of this experiment in this way also. No, let's say somehow we have certified local randomness. From there, we are certifying actually global randomness here.
Yeah, you can say that, but how you will get the certified local randomness? I know that this RI doesn't need to be private. Let's say from a beam splitter, you get a local randomness. So here, Alice is getting a local input randomness. Bob is also getting a local input randomness, and then they create a global private randomness. Yeah, one can also think of it like that. Yes. Because it is not apparently always true that if you combine two local randomness, it will give you a, I mean, let's say RIA is RJB. It does not guarantee that if you write it like that, RA, it is random or not, this sequence. Yes. For that reason, you need to be realistic. Nice one.
Okay.
So you see, that whenever a statistics violates spell inequality, it doesn't have any local ontic model. It is not predictable, and also the most important thing, let's say one can think of it like a radioactive cheating. That when I am doing the Bell experiment, I will just write down the sequence of the output, and I will program that sequence in the Alice and Bob box. So whenever Alice and Bob will start performing the experiment, was written in that sequence. But the thing is, with this pre-shared strategy, Bell inequality will not violate, because that is kind of a shared randomness is between Alice and Bob, and with that, Bell inequality will not be violated. So this is very also important point, that Bell inequality violating statistics are, that means inherently random and also private, and also there is no pre-shared strategy. Now one can ask that since let's say CHSH is a good measure of non-locality, at least in the 2-2 scenario. So one can ask, since CHSH violation is the necessary for certifying randomness, whether there is any link between them. For example, if more the non-local implies more the randomness, that kind of thing. So now we are to answer this question. Now we have to understand first that how we can quantify, because right now what I was talking about little more in abstract way. Now we have to consider how much randomness is present in a probability distribution. Now for that, let's start with some intuitive idea. Let's say I have a set of events, and each event occurs with some probability p, and since the events occurrence are random, that means no events probability will be 1. I mean, no events can occur with probability 1. So each element has to be like between 0 to 1. Now, what about, let's focus on the most probable event, which has the probability p max. Now one can see that if the minimum value of P max is always 1 by D if there are D number of events, and the maximum value of this P max should be 1, right? So if the value of P max is increasing, that means we can say it is going towards the more predictable distribution. So that means it has less randomness. So P max is a good marker that how much randomness present in a probability distribution, and you can see that this will give us the actually lead to the more secure bound in an adversarial sense. That's why we will take Emax as our quantifier. Now, if we want to express it in terms of entropy, to express it in bits, then we have to adopt a proper entropic measure which connects the Pmax in a entropic way, and that is called the minimum entropy. So it is a variant of Renyi entropy with this Renyi parameter alpha when tends to goes to infinite, and this Renyi entropy expression becomes it only connects the Emax in the probability distribution. So that's why minimum entropy is usually we take as a good quantifier of randomness. But one can say that anyway entropy measures some disorder or some unpredictability in a statistic. So I take Renyi entropy because I will now try to say that why this quantity is important in the security perspective, that Pmax quantity. Let's say if there is a Bell experiment involving Alice and Bob, and they are trying to create a random statistics. Now what will be the worst way they can face? I mean, what Eve can do with them, because Eve is selling the devices to Alice and Bob. So what Eve will try to create? Eve will try to prepare a tripartite state correlated with Eve, and between, I mean, the correlation should be there between Alice, Bob, and Eve, and when Alice performed this measurement, why it is coming? When Alice's measurement is this, Bob's measurement is this, and after Alice and Bob's measurement on row ABE, Eve will perform this POVM, maybe some D outcome POVM or whatever, in general one POVM on her reduced state to get some information about the outcome of Alice and Bob, like PAB XY. This is the observed joint probability by Alice and Bob, and it is like this. This is basically in H is the Hilbert space associated with the Eve state. And after this measurement by Alice and Bob, the reduced state of Eve will be, the unnormalized reduced state of will be AB XY. I will say it is Eve. This is basically nothing but you can write it that in this way. This should be something like this.
Sorry, Dibda.
Yes.
So you are assuming that Eve is space like separated from both of them?
Okay, one assumption is that that since the communication between Alice and Bob is prohibited, and also the thing is that Alice and Bob's labs are shielded, right? That means nothing can come out from Alice's lab or Bob's lab. Now how one can ensure that, I don't know. So that means
I
even if EV is space-like separated or not, it doesn't matter, because no information can go, no information can enter the Alice's lab and can come out from the Alice's lab.
Mhm. Yeah,
Okay.
I understand.
So actually here also there is a vicious cycle. One day I heard a Kolbeck talk and he was emphasizing on this assumption repeatedly, that Alice and Bob's lab must be well shielded and all that, so that no information can come out. So the question was that how you can ensure that. One way of ensuring is the no signaling, right? You put them in, you ensure that they are in a two different light cone, and the measurement time between Alice and Bob should be less than the time the information can reach from Alice's lab to Bob's lab if there is a leakage. So in that way, operationally you can ensure it. But I don't know. People sometimes doing the Bell experiment tells that no signaling is ensured because Alice and Bob's lab are shielded. And sometimes people are saying no signaling, Alice and Bob's labs are secured, that's why no signaling is ensured. And sometimes people say we 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 have considered the time between Alice and Bob in such a way so that the operationally no signaling is ensured. That implies Alice and Bob's labs are shielded. So I don't know which way is the more fundamental one. So in that way, it doesn't matter whether EP is space-like separated or not. That has no communication between them. That's the most important thing.
Okay. So, but then I'm saying that like, then why are we worrying about it? Because we are thinking that, okay, so how did Alice and Bob actually get this correlation? Maybe they buy it from some manufacturer called Eve, and then Eve is cheating to see. So he's giving this correlation to them in such a way that he can retrieve the information later, even though their labs are shielded. So that test they want to do, right?
Yes, because it can prepare, instead of preparing a bipartite state rho AB for Alice and Bob, it actually prepares a tripartite state rho AB, which is correlated among themselves, right? So whenever Alice will perform some measurement and Bob will perform some measurement, then each state will collapse in some state like what I'm trying to write down here. That this is the this is the overall reduced state. Okay. So whenever they perform some measurement, each state will reduce in here. Some state it will get, and this is the overall state. And from this, and then it can perform some POVM on a reduced state to get to guess the outcome E when it is equal to A and B. So I mean, if I write the Eve's probability, then it will be more clear that Eve's probability, Eve will try to guess this probability AB when she measures some Z and Alice got A, Bob got B, Alice measured X, Bob measured Y. And this is basically what? This is basically rho AB XY Eve M E Z, right? So in that way, it can guess the outcomes of Alice and Bob, right?
Okay, understood. But this one thing.
Yes.
So I have one question. This reduced state on the left hand side means like what do you mean by the overall reduced state? So if so it's not clear to me what is the meaning of overall reduced state.
Reduced state after Alice and Bob's measurement. So after Alice and, let's say Alice performs some measurement X, a definite measurement X and Bob's definite measurement Y. Then after their measurement, what will happen? The if state will be if state if state will be in a classical separation between Alice Bob's joint state, right? So
Yeah.
depending on what Alice and Bob is getting the outcomes with some probability, Alice and Bob's joint state is like that, right? So that's why I'm telling you that it is a reduced state after Alice and Bob's measurement. And then
Yeah, but
Hmm.
like it is the reduced state, but like what is the given there? Like given that Alice got, so see,
Yes,
AB
yes.
tensor this.
Yes,
So
given
that I,
this
yeah, given that,
PABXY, you can see that this PABXY is when Alice performs AAX, Bob performs BBY, this measurement, they will obtain the outcome AB, right? So in when Alice
yes,
obtains a outcome, let's say 0, Bob outcomes, let's say 0, and in between them, let's say the state is like 0, 0. So in that case, if state will be 1, that row 0, 0, 0, 0, E. This is one state,
hmm.
and this is the overall reduced state, right? Now E will
Yeah, but
perform the
yeah, but like you are doing the summation over AB, so that's why I'm confused. On the left hand side,
Uh,
should the AB index be there?
no.
You can, Sahil, you can think in that above equation when he is taking trace of row
Mhm.
ABE. So you just trace out AB, and
Yes.
then it is row ABE. Then there is a POBM, A given X, B given Y, tensor identity. Your row if AB given XY is that part when you are tracing out AB only.
Yes. Yeah. So AB tensor row if ABXY. This is the reduced state of if given that Alice has got an A
Given that,
outcome and
yes,
she did X measurement and all those things, right?
exactly,
Yes,
exactly.
yes,
But
yes.
now he is doing a summation over AB on the right hand side.
Yeah.
So
So
this is on
I
an
think
average
Yes,
state when you did the measurement X and Bob did the
why?
measurement Y.
Yes, yes.
So the left hand side should not have a AB index. That's
Oh,
what I'm
no.
trying to say.
yes,
Okay.
FXR should not be. Yes.
Yes, yes.
Yeah. Then it's fine. Yeah.
In the
This
left
is
hand
what
side,
my
it will only
confusion was.
depend on the what measurements Alice and Bob is performing,
Exactly.
and
Exactly. Okay.
eventually he will perform this POVM on her state and try to guess the outcome of A and B. Now, what extent it can guess? So that means this is just only one strategy, right? So to maximize
Yeah.
Eve's guessing, Eve need to maximize her guessing probability over all possible POVM he can perform. They can perform, right? And another thing is that, let's say after Alice Bob's experiment creates this behavior, right? P A B X Y. Now it comes from a specific strategy, that is row AB. Row AB is, I must write here. Row AB is this, okay? Yeah, row AB and some measurement strategy. It creates this. It creates this state row AB, and with that one behavior, Alice and Bob obtain, right? Now the thing is, this strategy is unique or not, because there exists maybe some other strategy also. They can create the same p vector, right? So which is in also in I'm only restricting myself inside the quantum theory, not the beyond the quantum theory. There may exist some other strategy also which can give the same p vector and even the same CSSH value, because at the end of the day they will also calculate this. They will also calculate the value of this, and this delta should be greater than 2. Beta is the CSSH functional, right? So for a given CSSH value, there can be many p vector, and I am only talking about only one p vector now, which can have different strategy. So to optimally guess the output of A and B, the Eve has to employ an optimal strategy also. That which strategy will give Eve the more edge to predict this outcome AB. So what we okay P. So I'm talking it as guessing probability G for measurement settings XY. This is basically P. Sorry, is P equal to AB I'm omitting the comma, when Eve measure Z, A, B, X, Y. First of all, Eve has to optimize this over all possible POVM Eve can implement, and also over all possible strategy that can give rise to this P vector. Let's say this one strategy, I denote it as a Q, and there are set of Q which can give rise to this P vector. So Eve has to optimize over all possible strategy also. And now this is the maximum guessing probability of Eve. This is the maximum probability which Eve can guess the outcome of A and B. And whatever be his, and after solving this problem, Eve will eventually find the optimal strategy, and Eve will always prepare the quantum state with this optimal strategy. So now you can see, to find a maximum on this is basically a semi-definite programming. And if someone want to optimize over all possible quantum realization, we have to apply this NPA hierarchy to solve this problem. Now, in this way, if one can solve the now this is the best guess it can do. So now we can say, okay, this is the minimum randomness that present in the P star. So it is linked with the, so we can maximize this again over the all possible choice of XY also, XY, NZ, Q, and eventually, and this P, A, B, XY. So if we solve this problem, it will actually give me the maximum guessing probability that it can have corresponding to this distribution P vector, such that and this optimization is a constant optimization, because we have to remember that beta of Q must be some delta, which is, let's say, write it in a more this way, some 2 plus delta, where delta is in between 0 to 1. 0 to 1 or 2 to minus 2, this will, whatever. Then we can actually first, in this way, what we are solving, let's see it geometrically. Yeah, I have. So this is the no signaling polytope, and since we know quantum mechanics has at least right now what the understanding is that quantum mechanics has a boundary like this. I mean, no finite number of extremal, and also we don't know whether all the boundary are curved or not. There are some results where they say that the quantum boundary is not always curved. There are some straight line, I mean, some plane boundaries there, but I'm not going into that. So this is your CSSH value. This is the CSSH value equal to 2. Now let's say in an experiment, the P vector I got, I mean Alice and Bob got, which is something like, let's say, 2 plus delta. So then the CSSH value is basically this, 2 plus delta. Now all the distribution on this 2 plus delta hyperplane gives the same Bell violation, 2 plus delta. And I don't know which one is the P vector. So it's now Eve's hand that what P vector she will provide to Alice and Bob so that her guessing probability will be maximized. So maybe Eve will provide this one. If found his maximum guessing probability comes from that, then Eve will create this distribution. Okay. Now that's why, to solve this problem, that what is the optimal guessing probability Eve can have corresponding to a given CSSH value, we need to optimize the probability distribution over all possible quantum realization and over all possible Alice and Bob's measurement and states. That means that all possible quantum realization means that all possible choice of measurement and state. So one can solve this problem numerically with using by solving this constraint SDP using the NPA hierarchy, and then one can plot this with CSSH value here and minus log 2g here. So minus log 2g, we call it as minimum randomness. That means R min. Because you can see in my previous definition, previously it was depending on xy. That means if Alice performs, let's say x1 a1 and Bob performs b1, then there is some guessing probability it can get. And if Alice performs, let's say a2 and Bob performs b2, then there is another value of guessing probability. Now, if I want that, forget about what measurement they are performing. Just if we look into this whole behavior, then what is the maximum guessing probability it can have? So then we have to also optimize our different choice of settings. So in that way, I can write it like that. Let's say R11 is basically minus log 2G11. In that way, I can write it. And finally, I can define R mean is equal to basically the minimum over all possible choice of XY, choice of pair of settings, and minus log 2G XY, right? Now, this we call minimum amount of randomness one can certify in a Bell violating statistics. And it is found to be, the relation is like that. It is Pironio has done this experiment, Pironio Nature 2011. Okay. Now you can see if we increase the Bell value more, it can get up to this point when the CSSH value is 2√2. And this point is called Cyrillson point. And because this point is unique, the behavior of this Cyrillson point is unique. This behavior looks like this. All the joint probability distribution is either 1/4 half plus 1 by 2√2 or 1/4 into half minus 1 by 2√2. If I write it in a box, you can see it more clearly. It is plus, 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 plus. So this is the Cyrillson point and it is unique. So if this distribution is unique, then there is no chance for Eve that she can create this distribution with some different strategy. Because people have shown that Cyrillson point self-test, the maximally entangled state, and anti-commuting measurement for both Alice and Bob up to local isometry. So whatever be the state and settings are, if in a experiment, if Alice and Bob observe 2√2 Bell violation, then they can be sure of one thing, that Eve doesn't have any strategy. Eve has to supply them this maximally entangled state and anti-commuting measurement. So there no optimization is involved, and one can just easily calculate the maximum probability for this behavior, which is nothing but 1/4 half plus 1 by 2√2. This is the guessing probability for Cyrillson point, and if I take minus log 2, it comes from down this point, it is 1.23 bit. And I am talking about here global randomness. Local randomness is how much? If we see the local probability distribution, we will see that for the maximally entangled state and the local states are basically I by 2. So Alice and Bob will always get 1 bit of local randomness. So if one can again plot the same thing for R mean for local randomness with CSSH value, one can get the similar kind of curve, and the maximum value will be 1 bit. So yeah, coming to that Sahil's point, what previously he told me, that with the local randomness, we are actually producing global private randomness. Yes, and you can see we cannot combine the local randomness to get a global randomness, because here in the
Souradeep, I think you have to pack up in 5 minutes.
Okay.
We'll open for questions, and you can continue.
Okay, maybe it's a good time to stop actually, because after that I intend to go into the more recent results and what kind of questions people can answer. But yeah, and I will just wrap it up maybe in 2 minutes. So yes, see, for the Cyrillson point, the local randomness are 1 bit, but global are not 2 bit. Global randomness is 1.23 bit. So now the thing is that 2 type of research people can pursue from here. Like if I give you a behavior, if it is not an extremal behavior of quantum, then you have to solve this optimization problem with SDP and NPA hierarchy, so that one can get the amount of certified randomness for a given behavior. And that technique, one can go through this paper. This reference is, I must tell, the reference is this, Nietosellars, sorry, CLRs, Nietosellars, NJP 16013. They actually solve this problem, that how to solve this SDP with NPA hierarchy. Another kind of research one can pursue, that just try to come up with some different self-testing statements, so that we can characterize many extremal quantum, and from there the calculation of amount of randomness is very straightforward, because there is no other strategy. We don't have to perform any optimization. We just pick out the maximum probability and can say it's done. But the difficulty with this, designing self-testing statements, are the difficulties. Maybe next day I will talk about with more intuitively that how one can construct such validity or this kind of self-testing statement to characterize the extremal distribution. Yeah, so basically you can stop here.
Okay, now we can take few questions. Okay, so if anybody has any questions, please ask.
Can you hear me?
Can you, Somkanjilalla? So I think your voice is not clear. Can you come closer?
Now can you hear me?
Yes.
Yeah, perfect.
Nice. Okay, so I'll go back to the statement about that, local randomness getting, with some amount of local randomness, you got more amount of global randomness, right?
Yes.
And can we say that the local randomness is ensured by the no signaling conditions?
What do you mean by that? I don't understand your question. Those are two completely different.
Like the amount of, okay, I'll try to make it a bit more concrete. Like in here, you are only considering the no signaling conditions between Alice and Bob, right?
Mm-hmm.
And so that no signaling condition between Alice and Bob ensures that the Alice and Bob are in space. You can imagine Alice and Bob to be in space-like separation, right? And Eve is measuring after Alice and Bob's measurement. So Eve is in a future light cone, which is like a shared between both Alice and Bob, right?
Okay.
So Eve, so like you will, then you also have a no signaling condition from Eve to Alice and Bob, right?
And that I actually ensured by the assumption that Alice and Bob's lab are sealed. I mean, if whatever Alice is getting the outcome, if it is leaked, then there is no concept of privacy, no concept of information policy, right? So that assumption is there. So that means no information can enter to Alice's lab and no information can go out to the Alice's lab.
Okay. So those are just local measurements. Okay.
Yes.
So so you have that, like implicitly you have also assumed that no signaling from Eve to Alice and Bob.
You can put it in that. Yes. I told you that this is kind of a vicious cycle. Someone tells shielding lab ensures the satisfaction of no signaling principle, and some experimentalist says that that they have ensured the no signaling principle by doing the measurement in certain time limit, so that their shielding of lab is ensured. But it's tricky. I don't know how to operationally test whether Alice's lab and Bob's labs are well shielded or not. But
So do you have a like general no signaling bound for this guessing probability with Eve, like with PR box?
Yes. Maybe next week when I talk about, I will go beyond quantum. Now Eve is restricted with quantum theory. If Eve is restricted with predictable theory, then in quantum mechanics, if it violates Bell inequality, it is very straightforward. But here we give the power to Eve that Eve can access the whole quantum domain. And maybe next week I will talk about when Eve get the power to access the beyond quantum theory, like general no signaling theory, then what will be his maximum guessing probability, or it will connect those questions, whether quantum theory is the maximal random theory or not, whether there exists another no signaling theory which is more unpredictable than quantum or not. This kind of question will come and we'll try to answer.
So isn't there any other way to ensure the local randomness? I mean, let's say you want to ensure the randomness of the measurement in the local sense. Isn't there exist any other local correlations, like apart from this Bell kind of correlation, which is for single particle?
Yes, it is all about you have to come up with a strategy. Like if you go into the contextual domain also, you have to derive that concept under the assumption predictability. For example, in a two-party scenario, I can take predictability and no signaling. For single system, you have to come up with a physical principle like that. Maybe retrocausality, you can go with that information cannot travel in past. So you take that assumption with predictability and try to formulate a contextual argument from there.
Is there any such results?
No. People have.
I mean, like you say, you show one
second.
Okay.
People has done using LGI or contextuality to apply randomness and just calculate the same thing. But the problem I found out in the fundamental aspect, that how you are ensuring that your statistics is random. I mean, it can violate LGI or it can violate a contextual inequality. It means something else, that your statistics does not have any non-contextual model, or this in LGI setup, the assumptions of those assumptions, you cannot create a pre-existing lambda theory, right? But the statistics is random. How you can ensure it? So that needs to be done first more carefully.
But as you have shown, this Bell function can be derived from locality and realism, but you have derived here with predictability and no signaling. Those are two statistical measures.
Okay.
So can one do this for the like the single particle level, like with some predictability and some other assumptions?
Yes, maybe. That's why I told you that maybe in the single particle case, one fundamental thing is the retrocausality, right? Information can transfer.
Yeah, backflow, maybe, yes.
Or maybe in a prepared measure scenario, you can put information causality also. But information causality is not, information causality also you can put there with predictability and try to see what kind of restriction you can derive. So local ontic derivation tells you that if a statistics violates CHSH inequality, there is no pre-shared strategy, right?
Yes.
But it does not guarantee whether your sequence is random or not.
Yes.
That's why we did a different interpretation of that statistics from the operational point of view. That you start with predictability assumption with some other physical principle, and then if it violates, then you can say that, okay, my statistics is now unpredictable.
Yeah.
And the other mathematics will be.
Sorry, please continue.
No, it's okay. Let's wrap it up for today. It's almost more than
I have one question.
Yeah,
which is regarding the definition of randomness. So suppose you have the two events. So I'm not going to check how this event is coming. I just want to measure the randomness of the event. Okay, so it is a p and 1 minus p, and then you told that take the max entropy or mean entropy, whatever it is. So you conclude that, okay, if P goes 1, then there is a no randomness. If P goes half, then there is a full randomness. And in that way, you come up to minus log P max, right?
Right.
Yeah. Now, what I'm asking, so suppose you have a classical coin, which is P1 minus P. Okay. Now you have a two pair of same classical coin. No? Okay, IID pair.
Okay.
Okay. Now, what will be the probability? So with the P square probability, it would be head-head. With P1 minus P probability, it is head-tail. And 1 minus P probability, it is tail. Yeah. Now, if you look carefully, that okay. First of all, if I exclude the event of head-head and tail-tail. And then right now I have only head tail and tail head event, which are actually equally random.
Yes.
So now I'm giving you a protocol where I'm just specifying a protocol where actually if I only look into this statistics head tail and tail head, actually I can secure 100% randomness, right? Log 2 amount of randomness, right?
Yes.
But only thing is that the probability would be 2p1 minus p. So can you write it to me?
What you want me to write? The head tail
amount of randomness we can secure here
is head tail probability is basically p into 1 minus p, right? 2 into.
And 2 into,
right?
Head tail or tail head. Okay.
Yes,
so
head tail or tail head. Whatever.
Tail head. So I think in this way we can actually secure 2p1 minus p amount of randomness.
Yes, you can, but the problem is the origin is the problem, right? Because maybe the sequence will be random.
That's right. I'm not asking the origin. Okay. Now what I'm asking, suppose if you just look into these things that if I measure the randomness with the original function, which is minus log of p max, then here it would be minus log of p square, right? Suppose let's p greater than half.
Yeah,
if you don't
it is just minus log. If p is greater than half, then
for a single coin it was minus log p. For a single coin it is minus log p, and for a two coin it is minus log p square.
Yes.
It is actually minus 2 log p.
Yes.
Now what I'm saying, the earlier we concluded 2p1 minus p, and now it is minus log p. I'm a little bit confused about this part. What is happening here? Which one is greater?
I mean, you have probability distribution p square 1 minus p whole square and p into 1 minus p into 1 minus p. This is your event probability, right? Now,
this is
if p greater than half, which one is greater? P square is greater? I don't know.
Yes.
Okay.
Yes.
Okay. P square is greater. So the amount of randomness present in this distribution is, one can say, minus log 2 p square. Now the thing is, just before I conclude this statement, that since it's a classical probability distribution and you know that the origin is not trustworthy and all that, so we don't have to bother about the adversary. So one can just quantify the amount of randomness by the sum over pi log pi, right?
Yes.
One can just calculate this, the average randomness, because in the before this device independent random number generation or quantum random number generator, people used to take this quantifier to quantify the amount of randomness present in the probability distribution. Now, when this adversary situation comes into play and adversary becomes more stronger and stronger, then we have to quantify the randomness in such a way that randomness for whom? I mean, it's for user or it's for adversary? For which perspective I should quantify the randomness? So minus log 2 p max, this is the worst quantifier in the perspective of user, right? Because you are losing so much information. But this is the best quantifier in the perspective of adversarial act. That adversary, in the worst case, adversary can goes up to only this. So you can trust your statistics at least that much.
Then when you are saying, let's I certify Bell-CHSH value is 2√2, okay?
Yes.
Let's I certify Bell-CHSH value is 2√2.
Yes. Then your probability distribution is either this, maybe there is a 2, I forget, but let's see, something like that, right? Half minus.
Yeah.
Maybe there is a 2, I'm not sure. Okay. So the probability distribution looks like this. It is either 1/4 half plus 1/2 or 1/4 into half minus 1/2. Now your average randomness will be something else. If you calculate minus pi log pi, this is your average randomness. But the problem is, if you use this randomness, adversary can guess more, because at some event, this event,
you already get 2√2. Bell-CHSH
yes,
already
yes,
get 2√2. There is no correlation with Eve.
No, there is no correlation with Eve. That is okay. That I agree. But if Eve is guessing randomly, let's say, Eve knows that Alice and Bob now get the selection point, so there is no strategy for Eve to manipulate. But Eve is trying to guess the outcome, which outcome he will always try to guess. The occurrence of this event, right? Occurrence of this event. Maybe let's say, I will give you an example. Let's say for first run, Alice and Bob, small a, small b. What I will guess for the first run, I will always guess this event. Let's say this is the probability of obtaining 0/0. Okay, whatever the settings are, this is the probability. I mean settings. Let's say 1/1, and I am guessing this. Now Alice choose A1, Bob choose B1. What I will guess? I will guess now the outcome is 0/0. Maybe I am wrong. But after a long run, you can see I am actually right most of the time, because I am guessing the most probable event.
Exactly. So that's why I think
when you will get the sequence more than, I mean, with higher percentage, I will guess the numbers in the sequence, right?
Yes. So I'm saying that's why I think always the random how much random it is defined by only minus log p max, not by the entropy.
Exactly. That's why
it
is the most reliable quantifier in terms of adversarial perspective. But this quantity is also important in some other respect, that how much, what I can say, spread is your distribution is. That your distribution is like a delta function, or your distribution is like that. This kind of answer, it can be easily seen from this type of quantifier, not from Pmax. From Pmax, you cannot get the whole idea about your distribution. So those two quantifiers has two different kind of meaning about randomness. This Pmax amount of randomness is basically connected with the adversarial perspective. And
okay, I have another question. I'll ask you more personally these things.
Okay.
But okay, I'm stopping asking questions. If someone has any other questions, we can take maximum another questions. Then we can stop the bit.
Okay.
I think
maybe there is none. So
there is none. Okay. Then we can
end
the meeting here, and we can continue from here.
Yeah.
Okay. Thank you all for your presence. Okay.
Bye.